Now we're going to look at constructions of labeled classes that involve trees. And if you took part one, you want to pay more attention here, where you didn't really cover this much in part one. So a definition of a labeled tree is just that you take a tree with n nodes, and there's various types of trees that we talked about in the last lecture. And it's the tree whose nodes are labeled with the integers 1 through n. Simple as that. But as we saw, so we might want to know how many different labeled trees are there of size n. And there's all kinds of variations that we're going to consider. As we did with unlabeled trees, is the order of a subtree significant? Is there a root? Is there a restriction on the degree of each node? There's an application called increasing, where we want the labels to increase along paths in the tree. So some of these questions are very easy to answer. Others are classic problems in combinatorics. But our point for this section is that all of them are easily answered with analytic combinatorics, or at least answered in a uniform manner with analytic combinatorics. Now, again, this is just getting through the terminology before we go to the specific of different trees. So when we talk about rooted, ordered, labeled trees, it just means that the order of the subtrees is significant. So we consider these two trees, for example, to be different. If we talk about unordered, then we consider those two trees to be the same tree. The order is not significant. But of course, if the root is labeled differently or something, then we consider those to be different trees. Those are known as Cayley trees. And there's applications for each one of these as well. If we take away the idea of a root, then say these two trees would be considered the same, because you can deform one to the other. They have the same labels on the middle node. But if they have different labels on the middle node, then we consider them to be different trees. And then we have the idea of increasing trees, where again the order is not significant, but the labels on the paths have to be increasing. And so these two would be different, because that path's got 1, 2, 4, 1, 2, 3, and that one's got 1, 2, 4. So those are examples of the things that we're going to be looking at. We'll also look at increasing binary trees, where order subtree significant, and everybody's got 0 or 2 nodes as children. So that's labeling the familiar tree structures that we talked about last time. So how many different labeled, rooted, ordered trees of size n? So there's 1 of size 1, there's 2 of size 2, and there's 12 of size 3. So that is, you take each of the possible trees, and there's 6 ways to label them. You just take all the permutations. In both cases, it's essentially a string of 3 nodes. And in fact, this generalizes immediately, so you can immediately see that the number of labeled rooted ordered trees of size n is n factorial times the number of unlabeled trees, because you can just take the nodes in the tree in any canonical order and just label them n factorial different ways according to that order. So that's a combinatorial proof of this, but we can also get it from analytic combinatorics, and it's worthwhile to do that. So again, we write down our class and our generating function. And what is a labeled rooted ordered tree? Well, it's a root and a sequence of trees using the star operation, that's all. So then, according to the symbolic method, the generating function is z over 1 minus L of z. That's the exponential generating function for labeled trees. That's exactly the same as the ordinary generating function for unlabeled trees. That gives us the Catalan numbers. But then what that means is, if we extract coefficients, then we take n factorial times the coefficient of z of n and label z. So that's n factorial times the Catalan numbers. That's the same as what I just said. There's n factorial ways to label a tree walk. And so just multiplying it out, you get a ratio of factorials, and we can use Stirling's or approximation or other methods to get an approximation for the counting sequence. But that's not our point for now. Our point is that the generating function equation for the exponential generating function is easy to derive from a simple combinatorial construction, z times sequence of z. All right, let's look at Cayley trees, which are the same except they're unordered. So we don't care about the order of the roots. So now there's only 3 ways to label the tree of size 3 with a root and 2 children. You label the root, and then we don't care about the order of the way the children are labeled. And then if you work through the different tree shapes of size 4, well, there's 24 different ways to label that one, but there's only 12 different ways to label this one. You can assign the root one of the 4 possible labels, and then you have 3 different ways to label the one below, and so forth. And what's interesting, if you add this up, you're starting to see powers, and actually the number of labeled root and unordered trees of size n turns out to be n to the n minus 1. Now, we'll talk about this proof later on, because these are special cases of what's called mappings, which is a more intricate combinatorial object. But we'll do this proof later on. For now, you can think of the structure as showing something interesting, that we get all these strange arguments on how many different ways to label things, but it all adds up to such a simple formula. And then we can look at increasing Cayley trees. So how many different Cayley trees of size n have increasing labels on every path? Again, we don't care about the order. In this case, there's only 1, 2, 3. There's only one way to do that one, and 1, 2, 3, 4, like that. 3 different ways to do this. So one's got to be at the root always. And then your children can be 2 and 3, but one of them, it depends which one gets the 4, or your children could be 2 and 4. But those are the only possibilities. You can't have children being 3 and 4, because then there's no place to put the 2. And so forth. So there's 6, and actually the number of increasing Cayley trees is n minus 1 factorial. And again, maybe not so easy to see where that comes from, but with analytic combinatorics, there'll be a uniform way to derive this. And then increasing binary trees. How many different binary trees are there with increasing labels on every path? So these are all the possibilities for a small number of trees. There's more binary trees because every node has, the order is significant, and every node has 0 or 2 children. Anyway, these are the possibilities, and there's actually n factorial different binary trees of size n. And again, this is an easy result that has all this structure behind it. It suggests a bijection, and actually there is a bijection between increasing binary trees and permutations. That's quite easy. So let's look at the analytic combinatorics of increasing trees. And in order to do that, we're going to introduce another construction called the boxed product construction. And this is just an example that the operations that we use in the symbolic method are not necessarily a closed set. It's not difficult to add more operations to respond to the needs of different applications. So in this case, the increasing facet of the application means that we need some combinatorial operation that takes that into account, and that's what boxed product is. So we're going to use the notation A equals B box star C. It means the same as star, except that we're only going to consider the subset where the smallest element goes into B, goes into the first one. So our little example of 1, 2 box star 1, 2, 3, out of these 10 possibilities, there's only 4 of them that have the smallest element from the first product. And again, the transfer theorem, which I'll give a proof in a second, if you do the box product and you have the generating functions for B and C, the generating function equation is A prime equals B prime C. So here's the proof of that. Just with combinatorics. So the number of elements in A, you can pick, you have to pick the smallest one for B, and then you can pick the other k minus 1 from n minus 1, and any one of these n minus 1 just k minus 1 ways. And then there's however many elements there are in B, and if there's k of them, then there's got to be n minus k in C. So that's an equation convolution that gives the number of elements in A. Divide both sides by n factorial and multiply by z to the n minus 1 and sum, and do the convolution and rearrange terms. Then we can separate into two different sums, and that's A prime of z on the left and B prime of z, C of z on the right. And it's not the proof that's important, it's how simple the transfer is. So let's check it for a small example. So again, this is 1, 2, box star, 1, 2, 3 is those four things. Generating function for that is 4 z to the 5th over 5 factorial. Generating function for B of z is z squared 2 factorial, and C is z3 over 3, like that. So A prime of z is multiplied by 5 times 4, z to the 4th over 3 factorial. B prime of z is z, and that checks. A prime of z equals B prime of z times C of z. So we have an operation and we have a transfer theorem. So then we can use that to enumerate increasing trees, like increasing Cayley trees or increasing binary trees. So for Cayley trees, it's a Cayley tree is z box star, a set of Cayley trees. And that just means z box star means the one has to go as the label of the root, and then the rest of them are labeled increasing trees. So from the transfer theorem, we immediately get the generating function equation, q prime of z equals e to the q of z. Now in this case, the first one, generating function is z, its derivative is 1, so it goes away, and then set's all left. Q prime of z equals e to the q of z. That's an equation that the exponential generating function of labeled increasing Cayley trees has to satisfy. And you can solve that differential equation. Log 1 over 1 minus z works. So its derivative is 1 over 1 minus z, and e to that power is 1 over 1 minus z. So that means that the counting sequence is n factorial times the coefficient of z to the n in that, which is just n minus 1 factorial. So that's a simple proof that the number of increasing Cayley trees is n minus 1 factorial using analytic combinatorics. Similarly, for binary trees, it's a z box times b, and that transfers to b prime of z equals b of z squared. And we can solve that one and get 1 over 1 minus z for that, which is a proof that the number of labeled increasing binary trees is just n factorial. Again, analytic combinatorics provides simple proof of these results without any kind of counting arguments. And not only that, it can be extended to handle situations where there's restrictions on the degree of the nodes and many other things. And by the way, increasing binary trees of bijection with permutations. Again, we don't always find bijections like this, but this one's an easy one. If you take a increasing binary tree and then you just flatten it, then you get a permutation. Or if you take a permutation, you take the smallest element, make it the root, and then do the same thing for the left and the right, you get an increasing binary tree. So that's an easy proof that increasing binary trees n factorial. Not so easy for Cayley trees. That's a classical problem in combinatorics, actually. Okay, so again, we start with the basic set of combinatorial constructs, and we can consider the analysis of all kinds of tree structures. And these are just a few of many, many examples of the study of labeled trees. It's a classical topic in combinatorics, but analytic combinatorics allows us to handle all of these things in a uniform manner. That's an introduction to the study of labeled trees using combinatorial constructions and the symbolic method to derive equations on generating functions.